Hello and welcome to the session. In this session, we are going to discuss how to compute gradient and directional derivative. We will also find equation of tangent plane and normal line to the surface. Let us first discuss gradient of a function z is equal to f of xy. The gradient of a function in two variables is a vector valued function of two variables. Let z be equal to f of xy, where partial derivatives of the function exist. Then the gradient of f is denoted by del f or del of f of xy, and it is found using the formula gradient of f equal to del f by del x I cap plus del f by del y j cap. The operator read as del is equal to del by del x I cap plus del by del y j cap, and del of f of xy is a vector in plane. Let us consider an example in which we have to find the gradient of a function f of xy equal to xy at the point 1, 2. Now we know gradient of f is equal to del f by del x I cap plus del f by del y j cap. So we partially differentiate f with respect to x and with respect to y. We get gradient of f is equal to del by del x of xy I cap plus del by del y of xy j cap, which will be equal to 1 into y I cap plus x into 1 j cap, that is equal to y I cap plus x j cap. Now at the point 1, 2, gradient of f is equal to 2 I cap plus 1 j cap, which is equal to 2 I cap plus j cap. Now let us discuss directional derivative. Suppose we have a surface given by z is equal to f of xy, then its slope in y direction is given by f sub y of xy, and the slope in x direction is given by f sub x of xy. Now if we want to find its slope at a point on the surface in any direction, then we will use directional derivative. The direction of directional derivative is given by the unit vector u. The directional derivative in the direction of unit vector u is denoted by d sub u of f of xy. The simplest method of finding directional derivative for a function z equal to f of xy, where f is a differentiable function, in the direction of unit vector u. Is by using gradient, which is d sub u of f of xy is the dot product of gradient of f of xy and unit vector u. If directional vector is not a unit vector, we have to make it a unit vector by dividing it by its norm. That is, if we have a vector u, then its unit vector u cap is equal to the vector u upon norm of the vector u, where vector u is equal to xi cap plus yj cap and norm of vector u is equal to under root of x square plus y square. Let us now consider the same example once again, which says that find the gradient of f of xy equal to xy at 1, 2. Now suppose we also need to find its directional derivative in the direction of vector 1 by 2 I cap plus root 3 by 2 j cap. So here we had already found that gradient of f is equal to 2 I cap plus j cap. So now we have to find the directional derivative of the given function in the direction of vector half I cap plus root 3 by 2 j cap. Let us denote this as vector u. We will have to first check whether this vector u is a unit vector or not. For this, we find norm of u, which is equal to under root of 1 by 2 square plus root 3 by 2 square, which is equal to under root of 1 by 4 plus 3 by 4, which is equal to under root of 4 by 4, which is equal to 1. So norm of u is equal to 1. Therefore, vector u is a unit vector. So to find the directional derivative of the function f of xy, we use the formula d sub u of f of xy is equal to the dot product of gradient of f of xy and the unit vector u. If vector a is equal to a1 I cap plus a2 j cap plus a3 k cap and vector b is equal to b1 I cap plus b2 j cap plus b3 k cap, then the dot product of vector a and vector b will be equal to a1 into b1 plus a2 into b2 plus a3 into b3. So here d sub u of f of xy is equal to the dot product of 2 I cap plus j cap and 1 by 2 I cap plus root 3 by 2 j cap. So this will be equal to 2 into 1 by 2 plus 1 into root 3 by 2, which is equal to 1 plus root 3 by 2, that is equal to 2 plus root 3 by 2, which is the required answer. Let us now discuss some properties of gradient. Let f be a differentiable function at xy. Then, if gradient of f of xy is equal to 0, then d sub u of f of xy is equal to 0 for all unit vectors u. The direction of maximum increase of f is given by gradient of f of xy, and the maximum value of d sub u of f of xy is given by norm of gradient of f of xy. The direction of minimum increase of f is given by minus of gradient of f of xy, and the minimum value of d sub u of f of xy is given by minus of norm of gradient of f of xy. Note that if we have a function in three variables f of x, y, z, where f is differentiable, then gradient of f is equal to del f by del x I cap plus del f by del y j cap plus del f by del z k cap, and d sub u of f of x, y, z will be equal to the dot product of gradient of f of x, y, z and unit vector u. Now let us discuss tangent plane and normal lines. Let z be equal to f of xy. We can write it as f of xy minus z equal to 0. So, capital F of xyz is equal to 0, where capital F of xyz is equal to f of xy minus z. Let f be differentiable function at the point P x0, y0, z0 on the surface S given by capital F of x, y, z equal to 0, such that gradient of f of x0, y0, z0 is not equal to 0, then the plane through P that is normal to gradient f at x0, y0, z0 is called tangent plane to S at P. The equation of tangent plane at P x0, y0, z0 is given by f sub x of x0, y0, z0 into x minus x0 plus f sub y of x0, y0, z0 into y minus y0 plus f sub z of x0, y0, z0 into z minus z0 is equal to 0. Line through P having the direction of gradient of f of x0, y0, z0 is called normal line to S at P. For example, if we have a surface given by x, y, z equal to 9, then capital F of x, y, z will be equal to x, y, z minus 9. We want to find the tangent plane and normal line to S at P1, 2, 3. So we first find gradient of f. Now as we know that gradient of f is equal to del f by del x I cap plus del f by del y j cap plus del f by del z k cap. So here gradient of f is equal to del by del x of xyz minus 9 I cap plus del by del y of xyz minus 9 j cap plus del by del z of xyz minus 9 k cap, which is equal to yz I cap plus xz j cap plus xy k cap. Now we find gradient of f at 1, 2, 3. That is, we put x is equal to 1, y equal to 2 and z equal to 3. In gradient of f, we will get gradient of f at 1, 2, 3 is equal to 6 I cap plus 3 j cap plus 2 k cap. Now, the equation of normal line at the point P1, 2, 3 will be in the direction of gradient of f at 1, 2, 3 and will pass through the point P1, 2, 3. Since the line is in the direction of gradient of f at 1, 2, 3, which is equal to 6 I cap plus 3 j cap plus 2 k cap, so it will have direction numbers 6, 3, 2. So its direction ratios are 6, 3, 2 and it passes through the point P1, 2, 3. So the equation of normal line is x minus 1 upon 6 equal to y minus 2 upon 3 is equal to z minus 3 upon 2. Using the equation of line passing through x0, y0, z0 and having direction ratios a, b, c is x minus x0 upon a equal to y minus y0 upon b is equal to z minus z0 upon c. We know that equation of tangent plane at a point x0, y0, z0 is given by f sub x at x0, y0, z0 into x minus x0 plus f sub y at x naught, y naught, z naught into y minus y naught plus f sub z at x naught, y naught, z naught into z minus z naught is equal to 0. So now the equation of tangent plane at the point P 1, 2, 3 will be given by f sub x at 1, 2, 3 into x minus 1 plus f sub y at 1, 2, 3 into y minus 2 plus f sub z at 1, 2, 3 into z minus 3 equal to 0. On putting the values, we get 6 into x minus 1 plus 3 into y minus 2 plus 2 into z minus 3 is equal to 0. This implies 6x plus 3y plus 2z minus 6 minus 6 minus 6 is equal to 0, which implies 6x plus 3y plus 2z is equal to 18, which is the required equation of tangent plane at P. So in this session, we have discussed about gradient and its properties, tangent planes and normal lines. This completes our session. Hope you enjoyed this session.